My name is Banu Tej Kumar. Today I am going to explain about the concept of error detection and correction of codes in switching theory and logic design. Now, concepts in error detection and correction of codes that we are going to cover in these coming slides are error detection of codes, error correction of codes, even parity, odd parity, Hamming codes, and problems on Hamming codes. Introduction. Error detection and correction techniques are essential for reliable data transmission in digital systems, as noise can cause bit errors during communication between two devices. To detect errors, we add one extra bit to data called parity bit. Means there are two types of codes: error detection and correction codes. Now, error detection and correction techniques are used to transmit data, and we can also use to eliminate noises between these from receiver side to transmitter side. And by using these techniques, we can transmit the code without any noise or without any disturbances and errors. So let us come to the error detection of codes. Error detection codes are techniques used in digital communication and data storage to identify errors that may occur during transmission or storage. Error detection codes are only used to detect the error and location of error, and for correction we use the correction of codes. Here detection helps us whether the code is having error or not. To detect the error in the code, example of detection of codes are parity bits and simple checksums. There are two types of parity bits: even parity and odd parity. Coming to even parity is a method of error detection where an extra bit called parity bit is added to a data unit, so the total number of ones in the unit is always an even number. Example, uh, coming to even parity, the given data should consist of even number of ones, then it is called as even parity bit. Let us take an example. The binary bit 10110, original data given is 10110. Here it is having 3 ones, so it is an odd number. Add parity bit to make the count even. A 1 is added in the corresponding LSB side. So finally, by adding 1 at the corresponding LSB side, we get the parity bit, even parity bit, as 101101, which is having 4 number of ones. So as 4 is an even number, so the given parity becomes even parity. Next, some examples for even parity bit generation. Decimal number 0 has message 0000, and parity bit parity P is 0, and for 1 it is 0001, and corresponding parity P is 1. For 2 it is 0010. For parity, even parity P is 1, and for 3 it is 0011, so having even number of ones, so parity P becomes 0. So for 4 it is 0100, and parity P here it is having odd number of ones, so parity P becomes 1. Similarly, and so on, for 6 it is 0110, and parity P is 0. For 7 it is having 0111, 3 odd number of ones, so its parity P is 1, parity P is 1, so and so on. We can check this. Yes. Finally, for 15F is equals to 15. For A, B, C, D, E, F, we take A as 10 and B as 11, C as 12, D as 13, and E, F are 14 and 15 correspondingly. So for A we take as 1010. Similarly, having even number of ones, so P is considered as 0. For F it is 1111, even number of ones, so corresponding P is 0. Now next, let us come to odd parity. Odd parity is similar to even parity, but odd parity is a method of error detection where an extra bit called a parity bit is used to a data unit, so the total number of ones in the unit is always an odd number. Here odd parity should consist of odd number of ones. But in even parity we should have only even number of ones. Similarly, like in odd parity we should have odd number of ones. Let us consider an example. Binary bit 1010. Original data given is 10 and 10, having even number of ones. So to change it into odd parity, we add an extra bit at LSB side. So corresponding by adding an 1, we get the corresponding data value as 10 10 and 1, which is having 3 ones, which is an odd number. So it is an odd parity. Similarly as even bit generation, odd parity bit generation is also considered. But for odd parity, when it comes to odd number of ones, the corresponding p becomes 0, and when it is having even number of ones, the corresponding p becomes 1. And as we can check that for 0 it's all 0, so parity p is 1. For 1 it is having only 1 0 0 0 and 1, so it is 1, so parity p corresponding p becomes 0, and so on. Like, okay, now let us come to error correction of codes. Error correction codes are techniques used to detect and correct errors in data transmission or storage, ensuring the recovery of original information even if some errors occur during the process. Error correction codes are used to identify the error position and use it to correct the position bit value. Here detection is used to only find the position of error, but in correction the code is changed, correction is done at the corresponding position where the error is originally present. For error correction codes, we use examples as Hamming code, Reed-Solomon code, etc. Hamming code. Let us come to Hamming code. Hamming code is one process of error correction of codes. Hamming code is a linear error correction code that enables detection and correction of single bit errors and detection of double bit errors during data transmission or storage. Formula: 2 power k greater than or equals to m plus k plus 1 is formula for Hamming code, where k is equals to number of random bits, m is equals to number of message bits, total number of bits are transmitted is equals to m plus k. Here total number of bits is correspondingly equals to m plus k. Now let us consider an example. Let us solve a problem to get better understanding of Hamming code. Consider for an example, encode the binary word 1011 into 7-bit parity Hamming code. The number of parity bits given are the number of parity bits we require to generate a 7-bit code is 3 parity bits. So 2 power 3 is considered as 8. So m plus p plus 1, as in our formula 2 power p greater than or equals to m plus p plus 1. Here 2 power p, we took p as 3, so 2 power 3 is equals to 8. M plus p plus 1, m is equals to number of bits, binary word bits given. These are m is equals to 4 and p is equals to 3 and 1. 4 plus 3, 7, 7 plus 1, 8. Therefore 3 parity bits are sufficient to generate the Hamming code, 7-bit Hamming code. Let us take the parity bits at the positions 2 power 0, 2 power 1 and 2 square. All parity bits are taken at the positions of powers of 2 only. So we took the positions as 2 power 0 as p1 and 2 power 1 2 as p2 and corresponding 2 square as p3. Now the ASTs d1, d2, d3 and d4 are the code given, so we place the code as 1011 as given above. Now step 3, determine the parity bits. We have to determine the parity bits, we use bit locations to determine the parity bits. Now to find the parity bit p1, we check the locations 3, 5 and 7. Now by using 3, 5 and 7, we find the parity bit P1. At the positions 3, 5 and 7 we having 1, 1 and 1. So it is having 3 ones, as therefore they ask to find as even parity. There are odd number of ones, so parity P1 must be 1 to become an even parity. So correspondingly, for to find parity bit P2, bit locations we have to check at 3, 6 and 7. At 3, 6 and 7 we are having 2 ones, which is an even number, 2 ones, so it is an even parity. So the position parity bit position P2 must be 0 to become 1, 3, 6, 2, 3, 6, 7 as even parity bit. Correspondingly, to find parity bit P3, we check the locations 5, 6 and 7. Here at 5, 6 and 7 we are having 2 number of ones, so the corresponding parity bit P3 must be equals to 0 to become 4, 5, 6, 7 as an even parity bit, even parity set. So enter the parity bits into the table to form a 7-bit Hamming code as 1010101 is the corresponding 7-bit parity obtained for the code 1011. Now let us consider an example for odd parity. Determine the single error correction code for the information code 10111 for odd parity. The number of parity bits required are 3 for even if it's all odd parity. Now let us check for 3. Parity bit P is equals to 3. As you can see, 2 power 3 is equals to 8. X plus P plus 1 is equals to 5 plus 3 plus 1 is equals to 9. 2 power 3 greater than or equals to 9. That is wrong. So we check P is equals to 4. 2 power 4 is equals to 16. X plus P plus 1, 5 plus 4 plus 1 is equals to 10. So 2 power M greater than or equals to M plus K plus 1, when we substitute in that condition, 16 greater than or equals to 10, it is true. So we take parity P is equals to 4 bits. The corresponding parity bits are at positions of 2 powers. So 2 power 0 parity 1, 2 power 1 parity 2, 2 power 2 parity 3 4, 2 power 3 parity 4 8. Now we substitute the given code at the positions of D1, D2, D3 and D4 and D5, and the parity bit P1, P2, P3 and P4 are kept empty. Now we are going to find the parity bits. To find the parity bits, here we take the locations as 1, 3, 5, 7 and 9. The corresponding one we should have to place the parity bit, as it's given an odd parity, so there should be odd number of ones at 3, 5, 7 and 9. As we can see, at 3, 5, 7 and 9 we are having at 3, 1, 5, 1, 7, 0, 9, 1. So we are having odd number of ones, so it is an odd parity. So P1 must be 0 to become an odd parity set. Similarly, to find P2, we check at position 3, 6, 7, 3, 6, 7. We have 2 ones, which is an even number, so even parity. So P2 must be 1 to become an odd parity set. Correspondingly, at P3, the bit locations are 5, 6 and 7. We have here also at 5, 6 and 7 we have 2 ones, so which is an even parity, even number. So to change into odd parity, P3 must be 1, and corresponding bit P4 checks at the location 8 and 9 must be 0 to have an odd parity. At 8 and 9 must be 0 to have an odd parity. So the corresponding parity bits entered from the table, the 9-bit Hamming code is 1 0 0 1 1 1 1 1 0 is the corresponding Hamming code obtained. Now let us consider another example. The Hamming code 1011011101 is received correct if if any errors. There are 4 parity bit hits. and odd parity is used. To construct a bit location, we have taken the parity bits as P1 2 power 0, P2 2 power 1, P3 2 power 2 and P4 2 power 3. The bit locations 1, 2, 3, 1, 2, 4 and 8 are parity bits, and the remaining positions are considered as D1, D2, D3, D4 and D5 as entered in the table. Check for the parity bits. P1 is checked at the location 1, 3, 5, 7 and 9. As it is an odd parity, there should be odd number of ones. At 1, 3, 5, 7 and 9 we are having 4 ones, so which is an even number. To change the parity bit into odd parity, we should have parity P1 as 1. We should change the parity P1. So there is an error here. We take the error as 1, LSB position error as 1 and keep it aside. Now let us check for the parity bit P2 with the locations 2, 3, 6 and 7, and the corresponding 2, 3, 6 and 7 we are having 3 ones, which is an odd one, so it is an odd parity, so corresponding error is 0. So there is no need to change these positions. Now let us go for parity P3. At 4, 5, 6 and 7 we can check 4, 5, 6 and 7 we are having 3 ones, which is an odd number, so it is an odd parity, so there is no error here. Correspondingly, at position for parity P4 we are going to check at the locations 8 and 9. Here also we are having 1, 1 which is an odd number, so odd parity, so corresponding error is also 0. The resultant word is 0, 0, 0 and 1, so the position at LSB is going to be changed. There is 1, so the location of error is 1, so it is changed as 0. Therefore the corrected code is 1011011000 is the corrected code, corrected Hamming code. And yeah, that's all. Thank you.